Ramanujan Institute of Technology. Today I am here to give a presentation about the topic particle in a one-dimensional infinite potential well. Introduction. Quantum mechanics explains the behavior of a particles at a microscopic scales. The infinite potential well is a classic model used to illustrate quantum confinement, and it also helps us understand particle energy levels with their behavior. The infinite potential well. A particle is trapped in a box with infinitely high walls within equations v of x is equals to 0 for where x is less than greater than 0 and less than L. The walls of the potential well are close to infinity, else the particle cannot exist outside the box. Physical interpretation. The particle is free to move within the well but cannot penetrate or escape the walls. This is a simplified model with clear mathematical boundaries. Schrodinger's wave equation, which is a time-independent Schrodinger wave equation. The equation is minus h cut square divided by 2m into d square psi of x by dx square is equals to e into psi of x, which is a second-order differential equation. Applies within the well where v of x is equals to 0. The boundary conditions for this are the wave function must vanish at the walls. That is, psi of 0 is equals to 0 and psi of L is equals to 0. These conditions lead to discrete quantized solutions. The wave function solutions. The following are the wave equations which are allowed. Psi n of x is equals to square root of 2 by L into sine of n pi x by L, where n is equals to 1, 2, 3 and so on. These represent standing waves. Let us see quantized energy levels. The energy levels corresponding to wave functions are En is equals to n square into pi square into h cut square divided by 2m L square, where n is the quantum number which represents positive integers only. The energy level in an energy level diagram, discrete energy levels increase with n square. The gap between levels increases as n increases. The continuous energies in a no continuous energy spectrum only specific values. Probability density. The probability of finding the particle is modulus of psi n of x whole square, which varies with position and energy levels. For example, higher energy levels to more nodes and more nodes to more complex probability patterns. The key observations are the energy is quantized. It also has no zero energy, which means the particle always has some motion, or which is also called as 0 point energy. In one-dimensional potential well, the particle behaves like a standing wave. Let us see the applications of the particle in one-dimensional wave. Quantum dots, semiconductors, and scanning tunneling microscopes. Let us see quantum dots. Quantum dots are nanoscale boxes which are used for electrons and semiconductors and nanostructures. The last application is scanning tunneling microscopes, which detects the quantum effects. Let us see the limitations. If we assume the infinitely high walls not physically realistic, which means we are considering infinite potential well, that means the high walls are uh, infinite, which are we assuming but not physically realistic. It ignores the particle interactions and external fields like electric field, magnetic field and various fields. It is still a powerful model for understanding confinement. Even though there are many limitations, it is still a powerful model for understanding quantum confinement. Now I would like to conclude the given our presentation with the 3 points. The infinite potential well is a foundational model in quantum mechanics. It demonstrates the quantization of energy and wave nature of particles. It forms the basis for understanding various complex quantum systems. Thank you everyone for giving me this wonderful opportunity. Thank you everyone.